Okay, so when we have a solar cell where we have the bottom layer we'll call ITO, which is the high work function electrode. Then we have our P-type material. We have our N-type. Now this is really just for organic uh, and nanostructured solar cells, organic, quantum dot, semiconductor, nanocrystal, that kind of thing. We're not talking about conventional solar cells here because the p and n junction works differently. But the basic principles of what I'm going to show are basically the same. So we have a source measure unit, sometimes an electrometer, called an electrometer. And what this does is it can source current and measure voltage or vice versa. And we attach the leads in this manner where we have the hot electrode here and the ground electrode up here. So when we apply a voltage and measure current, we get a negative current when electrons are headed from through the hot electrode into the device, and we get a positive current when positive charges are going from the SMU through the hot electrode into the device. The output from this is the short circuit current density and the open circuit, I'm sorry, just the current density and the open circuit, or sorry, and the voltage. And the particular points of intersection here are the open circuit voltage and the short circuit current density. Current density is usually given in something like milliamps per square centimeter, and the voltage is given in units of volts. This is the light curve, by the way, where the light comes in through the bottom of the device. So this is H nu for light. And we draw it in this manner. This is called the conventional architecture, where the transparent electrode is the one that transports the holes and through which the light first passes. When the light gets to the reflective electrode up here, this is the aluminum, then you actually get a second chance for the device to absorb the light after the photons bounce from the aluminum back through this way. So you probably only really have to have this be half the required thickness because you get two chances to absorb the photons. So that's really convenient if you have the aluminum be transparent. I'm sorry, be reflective. So in the dark, you get a curve that looks like this that passes through zero and then kind of rises like that. Didn't really intend to have them cross here. They might not, doesn't really matter. But this is the dark curve. So it's dark because at negative currents, at negative voltage, so negative voltage means you are applying you have a big negative charge over here, and then you're trying to shove it into the device through the p-type material. Now, the p-type material does not like transporting negative charge. So you're applying this big negative voltage out here, but you get a very small negative current because the p-type material is not inclined to carry electrons. Once you get to a certain point over here, where you apply a large enough positive voltage, the where you apply a large enough positive voltage, the you get to the point where you're putting in positive charges into the p-type material, and the p-type material likes transporting positive charges. Then when it gets to the interface, the negative charges kind of come out to fill in those holes, because in order for holes to move, electrons have to go backwards in the other direction. So then that is the way that the charge carriers want to go. So over here is reverse bias, and over here is forward bias. And okay, so once we turn on the light, the whole curve shifts down. And to understand what's happening when the curve shifts down, it's useful to think about various regimes of charge transport. So let's write these in red. So at a big negative voltage, we'll say we've got a big negative voltage here, but light is going in and charges are coming out. What charges are coming out at, say, this first region? Let's call this region 1 over here. So at region 1, there's a little positive charge coming out, because the solar cell is doing its thing. It's generating electron hole pairs. The positive charges are coming out of the p-type material. When negative meets positive, that draws more negative charge in than would go in if there weren't any positive charge here, and that's just because of a Coulombic effect. Like, you have some positive charge here and you have a big negative charge here. By the bigness, I mean the size of the voltage, the amount of energy in this charge, the potential energy in this charge. So we get even more negative current than we would in the dark condition, because we have this positive charge here that arose due to the fact that we're shining light on the device. Let's now think about region 2. And at region 2, we have no bias going in. So we have, let's say, zero bias going in, neither negative nor positive, but we still have this this positive coming out. Now, even though the bias here is zero, we're applying zero bias, we're still going to get current. Why are we still going to get current? And what charge is it going to be? It's going to be negative current, because this positive charge here is still going to draw current from the source measure unit, and that current is going to be electrons, because this here is positive, and therefore the device will give you a negative current in the output. Now let's look at, let's say, region 3, and region 3 is where we start to bend upward here. And now we have a little positive charge and a little positive charge. And what they do is they start to cancel out. They basically cancel out. If you have energy of the same, so these two charges here are the same size, you're trying, a lot of positive charges are trying to come out, and you're trying to shove positive charges in. So it's like a tug of war, but pushing, and nothing happens. No current flows, because you're trying to get positive charges in, positive charges are coming out, no current flows, and that's the scenario associated with the open circuit voltage. So down here, the current that was flowing with no applied bias. So that's current with no applied bias, and or a short circuit. So zero resistive load, no resistance in the load. So this is the same current that you would measure if you had just a thick copper wire connecting the two terminals of the device, and you were somehow able to measure the current without doing anything, without affecting the charge transport. That's the current you would measure. Over here, the VOC is the voltage at uh, voltage at zero current, or where resistive or at infinite resistance in the load. So if you're not getting any current at all, that's the maximum voltage. At some point here, you have a maximum power point, or the MPP, and the maximum power is the current density times the voltage that gives you the highest power in milliwatts per square centimeter. And you can define two boxes here. So the current and voltage at the max power point. The current and voltage at the max power point um, divided by the product of the open circuit voltage times the short circuit current density is the fill factor. And the fill factor you ideally want to be 100%, but it's never 100%. It might be in the 90s for a really good cell. Let's look at one more regime here. We'll make it yellow, and that'll be regime 4. And at regime 4, we have a very high energy positive charge. And again, we have a little positive charge here. Now, this positive charge here from the source measure unit overwhelms the positive charge coming out of the device. And then when this positive charge sees the p-type material, so it kind of like overruns the defenses here. It's like a castle with, like, knights on the outside, and then this positive charge just kind of overruns those knights and goes into the device. It sees the p-type material, and we're under forward bias, and it likes that. P-type likes carrying positive charges. So then the current is positive and off the charts, high, just like it is over on this side of the IV curve. So a couple of other things that you can consider. So the fill factor is the product of the is the max power divided by the VOC times the JSC. And the power conversion efficiency, sometimes you'll see this as the Greek letter letter eta, is you can write this as the fill factor times the JSC times the VOC over the power input. And that's the optical power input. That could be the sunlight. Now, the sunlight, so the power in, is the like the simulated or real solar power flux, and that might be something like 100 milliwatts per square centimeter. So a 1% efficient solar cell would give you 1 milliwatt per square centimeter, and so on up. This number is usually given by the AM 1.5G spectrum. And this stands for air mass 150% ground. And what does that mean? It means that if you have the Earth and the Earth's and the continents here, the Earth has an atmosphere that is however thick, and then the sun will shine light, and at the angle where the sunlight goes through 1.5 times the atmosphere, 1.5 times the thickness of the atmosphere. So this here is like uh, 1.5 times H. That's the amount of light coming through. Now, and this happens, I forgot the exact number. It's like 49 degrees from the zenith or something like that is the angle. Um, you can look this up, but it's like 40 to 50 degrees from the normal. And what does this G mean? So G means ground, and that accounts for scattering. So when you are outdoors and you put your hand out and you cast a shadow, is the space under the shadow completely black? Like, no. So you can still see the grass or the sidewalk or whatever. And all of that extra light is all of the extra light that comes from scattering from particles and molecules in the atmosphere, comes from trees, comes from snow, comes from whatever it is that's out there that causes things under direct it causes things in the shadow to still be lit. So that's the ground spectrum, and that is in contrast to the direct spectrum, which consists only of the light that impinges directly on the object in the pathway of solar irradiation. There are a couple of other parameters in the photovoltaic IV curve that are useful to consider. One of them is the series resistance, and the other is the parallel resistance. Technically, this is the parallel resistance, but the more useful way to think about it and the more useful terminology is the shunt resistance. And a shunt is a little bit like a short circuit, but not quite a short circuit. And the way that these are measured, so ideally, you want the series resistance to be as low as possible, and you want the shunt resistance to be as high as possible. Keep in mind we're talking about resistances here. So the series resistance the lower the resistance, the steeper the slope, because the resistance is the volts per amp. It's the bias per current, as opposed to a normal slope, which is rise over the run. So it's actually the inverse of the slope. So a low resistance gives you a steep slope here. A high resistance gives you a shallow slope here. Now, if your series resistance is, say you have a series resistance like this, then the best you can do with your curve is maybe something like that, or something where the fill factor is degraded and the short circuit current density is degraded. Similarly, if your shunt resistance is degraded, so it's lower than you want it to be, then all of a sudden your photovoltaic curve trajectory is more like this. And you, again, your fill factor goes down, and then your open circuit voltage can no longer be its maximum amount. So what are the characteristics that give rise to a series resistance or a shunt resistance? Let's consider an ITO film that does not have an exactly flat interface. This is just one example. Suppose that when you are depositing your ITO, it's very jagged like this. Then maybe you deposit your P-type material, and then maybe you deposit your N-type material over the top. Now, when you deposit thin organic or nanocrystal films or even films of photoresist, they tend to smooth out these asperities, but not entirely. It's a bit like a snowdrift. A snowdrift will still have the park benches and firewood and stuff. It'll have like impressions of them below it, even though the snowdrift tried to smooth out the asperities. So then when it comes time to evaporating your aluminum, you might have this region here where this part from this distance is actually very short. And this is called a shunt. It's almost a short circuit, but it's not quite a short circuit. It could actually be a short circuit. That would be an example of a shunt. And as a result, it's a lot easier to get charges through here than you want it to be. And therefore, your resistance at this location here is lower than you want it to be, and charges have no problem sort of bridging that gap and getting into the device with more facility than you want them to. So that's where the shunt resistance comes from. The series resistance, in part, comes from a lot of things, but one of the things it can come from is also from the electrodes. Suppose you have a device where your electrodes are kind of granular, and say your aluminum maybe is like kind of a broken film, and maybe it's really thin. Maybe you have like a really thin ITO layer, and then maybe your aluminum is really thin. This will have both of these scenarios would have high R series. Any of these electrodes being less conductive than you want them to be, and therefore they can't shuttle charge away from the device very well. And therefore, this series right here, this our series up here, would be shallower or higher resistance than you want it to be, and that could cause this limitation you see in the curve characteristic of high series resistance. The series resistance could also be a consequence of poor charge transport in the device layers themselves. Oftentimes, a bad fill factor. So let's say you had an IV curve that had actually fairly decent shunt and series resistance, but nevertheless, there was still some degradation in fill factor. That might be because you have a lot of traps in your N and P type materials or your charge carrier mobility is not very good. You might also have unbalanced mobilities. Those are things that could lead to bad fill factors, bad currents, bad resistances, and a lot of times in a really kind of lousy solar cell, you will have all of these problems, like the solar cell was like run over by a truck or something. It'll have a lot of defects in it all at the same time. So it's rarely a simple matter to tease out one thing versus another, but it is definitely possible to make a device that sort of intentionally has any one of these nanoscopic defects or these defects that arise as a result of nanoscale processing. Just one last thing I want to say here. So why do they have the words um, uh, parallel and series resistance? So let's take another 4-layer device, ITO, P, N, aluminum, and the say we've hooked it up to the source measure unit again, where let's put a uh, let's put a resistor in parallel with the device. Oh, that was interesting that it did that. um, and again, this will be our grounded electrode, and then down at the bottom is our hot electrode. This is our parallel, and then in another scenario, this would be our series. Or you could have them both in the same device. So like we could just as easily have drawn it this way, and then this would be our series. So you can mimic the effects of these nanoscopic effects on the series and shunt resistance by putting a um, uh, basically by putting a series or shunt resistance directly in contact or in line with the device.